What we're showing here is some interesting source code to give an understanding of how the E8Flyer is constructed and how the Lisi model is represented. As we can see here at the lower end of the screen, we have particle quantities for each parameter that generates particles. For example, the anti-parameter will multiply the number of particles by 2, the particle type also by 2. The counts here, as you can see, multiply out to a total of 256. The next set is actually the particle representation. For the fifth row, those are the excluded particles. The fourth row is an F4 configuration or an XV configuration. The third row is the weak and strong forces. The second row is the quarks, and the first row is the leptons. This is more simply represented in a particle type list that shows the particle type 0 and particle type 1 symbols. And the complete flavor list, which will show the generation or color generators for each of the rows and particle types. These are actually used to generate the symbology and reference individual particles in the particle selector. Now, putting these particles together is several lists. The E8 original list is basically Lisi's combinations with the added 16 particles for the exceptions, which are essentially the dimensional representation. The E8 bin is a coordinate system which I have added because there's a one-to-one correspondence between the E8 original and the 256 particles in an 8-bit configuration. As you can see, the permutations run a pattern from no ones to all 8 ones, and of course the 0 is an anti of the 1. Now, the theory of everything that I have created has a capability to predict particle masses and lifetimes, and this is done by a selection of constants and dimensions that define a fundamental unit of measure, which is very interesting in that it is represented by fine structure constant to some power to define each of the fundamental constants. That power is 8, corresponding to the 8 dimensions of E8. As we see, we define C as fine structure to the -8, multiplying that dimensionless fine structure by a length divided by a time, and converting it to meters per second, we get the speed of light. The conversion is a proper conversion based on the new units of measure. And of course, we have Planck. We have the h bar is simply the c times a mass unit and a length unit. Converting comes out correctly. The Hubble constant is also becomes fundamental, which is basically the inverse of c times 4 pi. And converting, we get a 71.58 kilometers per megaparsec per second. Newton gravitational constant incorporates some electroweak parameters and comes out accurately within the standard error. Combining all of these into a string of equalities that is true with proper conversions all relate to fine structure to the -8 multiplied by time. So time is the fundamental scale that as the universe expands. Now mass can be simply calculated. The Higgs mass is the square root of the 2 times the Planck with proper conversions. It comes out to 147.9 giga-electron volts. Electron charge shown here. The weak charge. We see we can define theta weak, the G and G prime, which are essentially cosine and sine. Solving for XW, you get a very simple alpha pi over 2, the square root, cubed root of the cubed root of alpha pi over 2, which comes out to be 0.112737. So calculating now the Fermi constant and the mass of the weak boson, 79.36, somewhat off, but very close. And the mass of the Z, 90.17. This error is primarily due to the delta from the Fermi constant, which I believe has some perturbative corrections. The mass of the electron is dependent on the generation, and so the calculation is shown here. It's relatively simple. It's all based on the generation that the particle is in will define which mass it gets, and the lifetime here is dependent on that mass. So in calculating the neutrinos is really just the inverse of that electron divided by a mass unit squared. Quarks, also very simple. Is the up or p-type 0 versus the p-type 1, also dependent on the generation. You can notice the patterns. And putting them together will assign all of those masses to the appropriate particles, and we have a very reliable prediction of particle masses associated with the Lee-Too model. I'd like to go into some of the metafavorite representations. The default representation for the model is E8, which gives a specific assignment to every parameter available in the model. So all of the other metafavorites derive as a delta off of that assignment. So E7 is simply assigning a data set or coordinate assignment to the physics coordinates, selecting a favorite projection of number 18, and then showing the edges. Favorites, you can see, simply set the H, V, and Z for